Uh, Tips. So I guess it's the last, I guess, of several LLZK compiler library talks the last 2 months. And so today we've got the equivalence checker for the class, which we worked on, and it's pretty much that LLZK, which Raghav will tell us all about after.
Right. Hi, I'm Raghav. I'm a formal methods researcher here at Paradise. Just a little bit of background about me. I got my PhD almost a year ago from Purdue, where I worked on applying PL and compiler techniques to like homomorphic encryption type stuff. And now I work on applying PL techniques to zero knowledge proofs. So on that note, today I'm going to talk a little bit about LLEQ, which is our new equivalence checker tool for ZK circuits. And I think maybe we'll have time to take like questions at the end or something, if that makes sense. Okay, so maybe I'll start by giving some motivation for what LLEQ does. So our goal at a high level is to verify that ZK programs are sound. In other words, that the constraints of the proof sort of faithfully capture the computation that you're performing. So a lot of soundness bugs are downstream of issues with determinism, which people are probably already pretty familiar with. But as you can see, there's a lot of other ways that the witness and the constraints of a proof can sort of fail to match up. So maybe we can take a look at this example here. This is just a fragment of circom. And in particular, you can note that like everything here is deterministic, right? So it's expressing something along the lines of the output equals the input divided by this like constant weight. But you can see that the way the witness generator does this is with like integer division, which is like truncating division. Whereas the constraints are expressing this as like multiplication in the underlying prime field. And so clearly, like these, everything's deterministic here, but like these two still have like different semantics, right? So for example, for an input of 1, the witness generator is going to truncate 1 over 10 to the 6th and produce an output of 0. Whereas the constraints are going to sort of require that the output is like whatever the inverse of 10 to the 6th is modulo p. And so this means that like an honest prover who tries to run this proof is going to produce a witness that like fails to satisfy the constraints, and so they're going to fail to produce a proof. Whereas like a malicious prover is going to be able to claim that like the output should be a lot higher than it should be or whatever. And so, obviously this kind of thing is bad, and we want to be able to, catch these sorts of bugs, or we want to like prove that our proofs don't have issues like this. Another nice consequence of proving equivalence here is that if later on you want to verify like some other semantic property about your proof, now that you know that the witness and the constraints are equivalent, it suffices to just verify this over the witness generator. And so in particular, now you're just like verifying some property of like an ordinary program, and you can sort of use more classical verification techniques there. So equivalence is kind of the thing that I'm going to focus on in this talk, but I do think it's worth noting that the way that we end up modeling equivalence means that our tool also proves things like determinism. Okay, so the example that I gave on the previous slide was circom, but in practice, the thing that we're verifying isn't actually circom code, so we're going to be verifying LLZK-IR here. Now, there's a few good reasons here. First of all, verifying LLZK means that we get to take advantage of a bunch of the like analyses and transformations and stuff that are already built into MLIR and LLZK basically for free. Working at this like intermediate level instead of using like one of these higher level languages means that we don't have to build a new verifier for every new ZK language that comes along. We can just use one of our front ends to lower it to LLZK and then sort of treat that as like a single like common interface for verification. And then finally, kind of on the other end of the spectrum, instead of going all the way down to something like R1CS, working with LLZK means that we still have access to nice abstractions like structs and struct parameters and so on. And so our verification can be kind of like modular, like one struct at a time or whatever. And so some things get a little bit easier that way. I will point out, I guess, that one challenge of doing things in LLZK instead of using one of these higher level languages is that, for example, languages like circom kind of naturally produce programs that are pretty amenable to good product alignment, so good like alignments between or correspondences between like the witness generator and the constraints. But in LLZK, we kind of have to discover these alignments ourselves. I'm mentioning this now because it's going to come up a little bit later, and so I'll call back to it when it comes up, I guess. But okay, so with the intro out of the way, maybe we can start talking about how the actual verifier works. So I'm going to use this template here as an example, this decomposed product. You can find this example in the LLEQ repository along with like a whole bunch of other examples, and I'll give the link to the repository at the end. But basically, this is taking two arrays of 8-bit numbers, so that's U8X's and U8Y's, taking their products like point-wise or element-wise, and storing that in U16s, and then it's kind of breaking each product down into the lower and upper bytes. Now, as I said before, we're not actually verifying the SIRCOM code directly. And so on the right, I've shown like a kind of simplified version of some LLZK code that corresponds to the SIRCOM. Now, you don't need to read all of this, but the important piece to notice is that we've sort of projected the SIRCOM out into a compute function that represents all of the witness computation, and then a constraint function that represents all of the constraints that we're emitting. And then we're taking all of our input signals and just passing these arguments to the functions. Okay, so we have these two functions. We want to prove that they're semantically equivalent. Specifically, equivalence here means that the signal valuations that the witness generator produces are going to correspond exactly to the valuations that are sort of accepted by the constraints. The way that we're going to model that is by taking two copies of each struct member. So kind of like duplicating all of these, where one copy is going to represent the value that's being computed by the witness generators, that's tagged with like an _W, and then one is going to represent the value that's being constrained with like the _C. Now that we have this, all we can just sort of check that the witness and the constraint versions of each signal always agree. Now, as I've said before, note that this is like a little bit stronger actually than the usual notion of equivalence. So in particular, if the witness or the constraints are non-deterministic, like technically they could still be equivalent if the sort of sets of values are the same. But here we're going to sort of flag this as an issue because there will be like at least one pair of values that don't correspond. And so yeah, sort of like modeling things this way means that if there are also determinism issues, we will catch those. Okay, so we want to prove that the witness and constraint versions of each signal are the same, right? For some signals, it turns out that this is really easy. So for example, if the constraints, if you ever emit a constraint that looks like assert that some signal equals some expression, all we have to do is go back to the witness generator and check to make sure that you're writing the exact same expression to that signal. So the way we do this is we can start by sort of tracking symbolic expressions for each value in the program, and then prove equivalence at this sort of like symbolic level on whatever signals we can. For scalar valued signals, it turns out this is just like doing the obvious thing, right? Checking to make sure that the symbolic expressions associated to the constraint and the witness are like literally syntactically identical. For array valued signals, you have to check point-wise equivalence. So like the entries at each index are the same. And then you also have to make sure that the set of indices that are written to or constrained are the same. So here the symbolic store lets us prove that like the U16 signal is equivalent because it's, you sort of have this pattern of like writing a value and then constraining that it equals that value. But the symbolic store tells us nothing about the lower or the high bytes because the way that the constraints there are expressed are like sort of like reconstructing this thing. Yeah. Okay, so as I said, the high and the low byte arrays, the witness and constraint computations aren't syntactically identical, and so the symbolic store isn't going to be enough to prove equivalence. And so we have to kind of fall back to some more standard deductive verification techniques. I know that this might be super familiar to some of you, but maybe for the others, I'll give a brief overview of deductive verification. So we start by representing the specification that we want to prove as this Hoare triple, so P, S, Q, where you can think of P and Q as being some like predicates, and S is some statement or some program. And you should think of this Hoare triple as encoding the fact that if P holds as a precondition before executing the statement, then Q will hold as a postcondition. Now, in our case, the preconditions are usually trivial, so just like true or empty or whatever. But you can imagine that you have some like interesting preconditions on the inputs or whatever, and so you could that would be something that you could put there. All right, so given a Hoare triple, we want to sort of automatically verify that it holds, right? And the way we do this, the idea is you start with the postcondition Q and the statement S, and you want to derive some other precondition, we'll call it like P prime, such that first of all, P prime SQ holds, so that like P prime is a good enough precondition to imply the postcondition after executing the statement. But you also want P prime to sort of be as weak as possible. So informally, that just means that it's not asserting anything that it doesn't need to, or it's not constraining anything that it doesn't need to. Formally, it means that it's like universal with this property. So like any other precondition that would work kind of factors through this or implies P prime somehow. Okay, so once we have this weakest precondition P prime, all we have to do is check that the actual precondition that we care about, P, implies P prime. So the statement that P implies P prime is what I'm going to call the verification condition, which is basically the thing that we have to prove to show that the Hoare triple holds. And in practice, we're just going to send this off to like an SMT solver or something. Right. So the nice thing about modeling things with weakest preconditions is that we usually have these like nice predicate transformers that sort of let us directly compute what the weakest precondition should be, given some postcondition and some statement. So I've shown here some examples of like Hoare logic rules and their corresponding predicate transformers. So for example, the weakest precondition of an assignment is just doing substitution, so substituting the variable for the expression in the postcondition. For conditional, you just look at the preconditions of each branch and then you sort of guard them based on the condition. For like the sequencing rule says that the precondition of like the composition of two statements is just the precondition of the precondition and so on. All right, so with that in hand, we can maybe go back to our example. So our basic verification strategy here is going to be to start with a postcondition that says that all the signals we care about are equivalent. And then we're going to use weakest precondition to derive our verification condition. And then we'll discharge that to an SMT solver. So more concretely, we're going to translate the semantics of the witness generator and the constraints into SMT formulas. So for example, a write to a particular witness a write to a signal in the witness generator is going to turn into an assertion that that signal equals the expression that's being written. A constraint is going to turn into an assertion that the two sides of the constraint are equal. And you'll note that like all of this is happening like mod P, or like mod whatever the prime field is. Then we're going to add assertions for all of the equivalences that we proved in the like lightweight static analysis step or the like symbolic store step. So here you can see that because our symbolic store already shows that U16s is equivalent across like the witness and the constraint, we can just add that assertion here, so that the solver doesn't waste time trying to like rediscover that fact. And then the verification condition is essentially just going to ask the solver to like find counterexamples where the witness and constraints might differ. Now, an unsat result here means that the solver couldn't find any counterexamples, and that means that the signals have to be equivalent. A sat result means that the model is going to give us an explicit counterexample of where the signals might be different. So like unsat is the thing that you want to see. All right, so on the previous slide, we kind of just looked at the loop body to prove equivalence between all of our arrays at like some generic index I. To extend this to pointwise equivalence of the entire array, this means that we have to start paying attention to the shape of the loop, not just the loop body, which in particular means that we have to start dealing with like loop invariance. So let's take a look at what weakest precondition looks like for that. So if you have a loop like while B do S, S is like some statement in the body of the loop, B is some Boolean condition. A predicate N is called an invariant if it holds at the start of the loop. And whenever it holds during one iteration, it also holds during the next. And so in particular, this means that by induction, it holds on every iteration of the loop, no matter how long it runs. And so this means that if you know that you have an invariant for the loop, you know that the loop invariant will hold when the loop exits. And so you can just use that to try to prove the postcondition. So when we calculate weakest precondition for a loop, we're going to kind of do this backwards, right? So we'll start by guessing what the shape of the invariant is. This is kind of the hardest part, but here we're going to assume that the invariant always has the same shape. So we're going to assume that it always looks like, for all x, whenever x is in bounds for the loop, then some signal at x is equal to some other signal at x. So we've conjectured this thing. We have to show that it is actually inductive. And so we're going to assume that it holds during one iteration and then use that to show that it holds during the next iteration. This basically amounts to showing that if you know that two arrays are equal up to a certain point, and then you run one more iteration of the loop, then you can sort of extend the domain over which the arrays are equal. So if you know that they're equal up to n, and then you run another iteration, then you can show that they're equal at n plus 1 or whatever. And the idea is that like because the arrays are finite, right? By induction, you can show that the arrays are now equal everywhere, or at least everywhere touched by the loop. So this is basically another Hoare triple that we have to prove, and so we're just going to recursively use weakest precondition to try to prove this. Okay, so now that we have something that we know is a loop invariant, we have to make sure that it's actually strong enough to prove the post condition that we care about. So in other words, like knowing that the arrays are equal everywhere that the loop touches is enough to show that the arrays are equal. So we check that the invariant at the end of the loop implies the post condition that we have. If it does, great, we're done. If it doesn't, we have to try strengthening it. So like adding some more assertions or like adding some more facts to the invariant and then doing this again and then sort of like, yeah, trying again until we get something that's strong enough. Assuming we get something that's strong enough, like I said, we're done. All that we still have to check is that the invariant holds at the beginning of the loop, because if it holds at the beginning, then it'll hold throughout because it's an invariant. And then assuming the loop terminates, it'll hold at the end. And then we already know that it'll imply the post condition if it holds at the end. And so the verification condition we generate is just the claim that the invariant holds at the start of the loop. It's worth pointing out that because we have to conjecture these loop invariants, and loop invariants aren't unique, like one loop might have like any number of predicates that actually satisfy the invariant property. The thing that we get might not actually be the weakest possible precondition. So like there might have been some other invariant that we could have guessed that would have been better. And so in particular, that means that like this procedure isn't really complete anymore. So we might sometimes fail to find the right loop invariant. But the idea is like with heuristics or whatever, we sort of do the best that we can. All right, so let's move back to our concrete example here. So remember, to deal with the loop, we have to conjecture an invariant. To help us out here, we're going to look at what signals the loop body refers to. And in particular, this means that since the loop invariant has to be able to talk about both the witness and constraint versions of the array, we have to start by, like, we need to have a loop that talks about both, right? So in particular, we have to fuse the loop in the witness and the loop in the constraint. We have to fuse these together into a single loop. And so this is where that product alignment thing comes up again. Circuit programs are kind of already very nicely aligned in this way. Like you can just write one loop that does both the witness and the constraints. But with LLZK, we have to do a little bit more analysis to try to figure out which pairs of loops should be fused. So on the left here, I have this sort of product program that LLZK infers. So you can see that we've replaced our separate compute and constraint functions with just a single product function. And now we have just one loop that talks about both low W and low C, and it talks about both high W and high C. And so based on that, we can conjecture an invariant that basically says that the high and the low arrays are equivalent up to the current iteration. And then we can use that invariant to extend the pointwise equivalence that we proved before into equivalence across the entire array. Now, again, this works, right? Because the size of the array or the bounds of the array are exactly the bounds of the loop. And so the piece of the array that the loop proves equivalence for is the entire array. And so like the invariant that we get is like strong enough to show the thing that we care about. Okay. Now, because loop invariant inference is kind of heuristic based, sometimes if the loop is too complicated or if it has a different shape than what we're expecting, loop invariant inference might not do a great job. So in those cases, we can just kind of fall back to trying to just unroll the entire loop, scalarizing all array accesses, and then just verifying the loop-free struct the same way that we were doing this before. So in this case, we can only do this if we have a concrete instantiation of the struct. So it means like here we need to know the value of this parameter n, because that tells us how much to unroll the loop by, and that tells us how big the arrays are and stuff. But once we've done this, once we've unrolled it, or like flattened everything, the SMT queries that we generate aren't over some generic array index I, but instead we have an assertion that says that the arrays are equal at index 0, an assertion that says that they're equal at index 1, and so on. And then we can pass this off to our SMT solver just like before. And if we get unsat, it means that they're equal everywhere, because we've like explicitly asked for them to be equal everywhere. And if we get sat, then the counterexample is also going to tell us like exactly where they might be different. This is pretty nice. Of course, the downside is that, first of all, the query is a lot bigger since now we have to refer to every element individually. And second, this means that we've only verified like this particular concrete instantiation of the struct. So if there's a soundness issue that like maybe only shows up in the array size of the multiple of 3 or something, then it's possible we'll miss it if that doesn't show up in this instantiation. But it's worth pointing out because this is like a particular mode that the tool supports. All right, so before I get into the demo, I figure I can maybe give a few notes about our tool chain. So as I mentioned before, we use MLIR, or I guess LLZK, as our target for verification. having a nice common IR is like obviously good for the reasons that I talked about earlier. But another nice side effect here is that in MLIR, basically everything is in SSA forms, like static single assignment. And that makes a lot of verification stuff easier because you don't have to worry about like variables being overwritten and then like figuring out where the definitions are and stuff like that. Specifically, within MLIR, we use the SMT dialect to kind of lower LLZK programs into SMT, like give them semantics into SMT before emitting SMT lib queries for the solvers. And then speaking of solvers, we use Z3 to automatically take care of all of the intermediate queries that we generate. So that's like, proving that something is a loop invariant. And then we use both Z3 and CBC5 to discharge the verification conditions that we generate. We're mostly encoding everything into the theories of like integers and arrays here. So we're not dealing with like bit vectors or anything. We also currently don't support like the theory of finite fields, since the witness computation in particular can contain like non-native operations that are sort of harder to express directly over finite field arithmetic. So like integer, like truncating division that we saw in the example, or like ordered comparisons like less than or greater than aren't things that necessarily make sense over FP. All right. With that, maybe we can move on to the demo. So I'm gonna stop sharing here, and then let's see. What's the right way to do this? Is there a way for me to share like my terminal screen?
Yes, you can usually choose the window from which you share.
Window, I see. Perfect.
Which actually is usually more stable than just sharing full stop, like sharing everything.
Oh, okay. Yeah, that's good to know. Okay. I guess can people see the terminal? Like if I type things here, does that show up? All right, sweet. Okay. So demo. So I have the LLEQ repository checked out here. I guess one thing it's worth mentioning is like right now, everything that I've talked about is in this like public release branch. We're working on getting all of that merged into main. It's just like modulo some code reviews and stuff. So hopefully that'll be in main soon. But yeah, so it's here. You can use Nix build. You can also build with CMake. I mean, right now I already have it built, but just like the standard like CMake configure and CMake build should also work. So you can see, I think the build also just like puts it in my path. So we've got the tool here. Maybe I'll start by reviewing the like interface. Actually, is this like readable? Should I zoom in or should I like increase the text size at all?
It's fine for me, but I have a pretty big screen. So if anyone is on a smaller screen, they might want you to zoom in a bit. That seems good, yeah.
Okay. Is this better? Yeah, okay. Okay. So yeah, so we'll just use help to see what this looks like. Okay, so the general syntax for using LLEQ is LLEQ. You have to give it one of these subcommands. This is like the mode that it's running in. There's a handful of options you can pass it, and then just the LLZK file that you're verifying. So the modes here, there's a couple of debug things. So there's dump store builds just that like symbolic store that we talked about with the like lightweight static analysis. And it builds that and then it prints it out. There's dump SMT, which will like generate the SMT encoding for the struct that you have, and then just like print that out, and it won't do any verification. There's the verify pathway, which is the sort of like flattened, just like given a basic block, generate SMT for it and verify that. And then there's, I think, the interesting one, which is the weakest precondition stuff, which like actually will take care of like loop invariants and like all of that stuff. Some generic options that you can pass to these. So a lot of the things require you to for example, anytime you're lowering to SMT, you have to know the like characteristic of the prime field so that you can like reduce modulo the correct thing. And so like LLZK modules do support having like the fields in the type of the like finite field element or whatever. And so sometimes like you can just infer what the field should be from the module. If the module doesn't have the field embedded in the type, then you need to pass the field as a parameter here. There's also this flatten option, which will do the thing I talked about of like trying to unroll all loops and like scalarize all arrays and stuff like that. And then most of these, because we're doing everything like one struct at a time, and you like a module can contain a bunch of different structs. So most of these require you to pass in like the struct that you want to use as an entry point for verification. Okay, so that's kind of the interface. There's some options for like these subcommands that you can also like verify help, and you can see like the verify thing also supports like a couple other options or whatever. So yeah, maybe we can actually look at this running. Okay, so I have a this is what the LLZK front end generates from some shortcom that just does like addition over the like baby bear curve. And I figure we can start by just looking at the symbolic store that this builds. So I'll do LEQ, dump store, and then my terminal, let me zoom in, yeah. My terminal wants to autocomplete this for me. So, okay, so LEQ, dump store, we've given it the name of the file, and then we've passed in the struct baby add is sort of the main struct to use here.
So I don't see things happening in your terminal.
Mm-hmm. Oh no. Wait. It only shares one terminal tab. That's fun.
Yeah, so now I can see it.
Okay. Yeah, okay. Thank you for calling that out, I guess. Okay, so yeah, this is the LLZK that we're going to verify here. Again, you don't need to read all of this, but this is just what the front end generates for like a circom program that does addition over baby bear. So in particular, you can see that like we have our main struct baby add, and then we've got like X out and Y out as our like main outputs, and then we've got these like 4 intermediates, beta, gamma, delta, and tau. Okay, so let's build this symbolic store and see what that looks like. So LEQ dump store is the subcommand, baby add.lzk is the file, and then I'm passing it the top level struct to use. Now here, because the symbolic store doesn't actually care about like explicitly reducing things mod p or whatever, it's just building these symbolic expressions. We don't need to know what the prime field is, and so you don't have to pass the field parameter. Okay, so if I run that, you can see it builds the store. For example, you can see that like, so there's an entry for like delta W is like this multiplication of this add of this multiplication of like, or whatever, you know, it's this expression. Delta C you can see has been constrained to be the exact same expression. So in particular, the store would be able to prove that like the delta signal is equivalent across both, and like same with tau and same with beta, and actually same with gamma across witness and constraint, because they're syntactically equivalents. But you'll notice that like we have this entry for y out W, but there's no entry for y out C, because whatever the constraints look like over y out, it's like the constraints don't look like y out equals some expression. It's going to be like some expression of y out equals some expression of something else or whatever. And so the symbolic store isn't going to be able to like pick up on that. So that's what that looks like. We can actually try to just like verify this, where now here I am going to need to pass the field. You can see it does some like SMT lowering. And then here it's kind of like struggling with this, but if you notice, like the verify command has like this enable store parameter. So if I turn on the symbolic store, you can see that it proves the things that the store was able to prove equivalent, and then it kind of like it struggles with some of the finite field arithmetic or whatever. But okay. Let's take a look at the weakest precondition verification pathway on our like running example of decomposed product. So just to remind, I have the circom here. This is, I guess, the same thing that we saw before, right? You just have these input arrays, you compute their product, and you break it down into the high and low bytes. And then I can show you what the LLZK for this looks like, but it's, yeah, it's there. So let's try to verify this. Again, I'm just going to copy the command so that I don't make a mistake typing it. But we're doing LLEQ. We're running this with weakest precondition over the LLZK file that we care about. We're passing this top level struct that we want to verify. Here, again, we have to give it the field, so we're going to use baby bear. Then I have a flag just to print out some debugging info. And then weakest precondition is going to sort of print out the verification conditions. So you could just like pipe this directly to an SMT solver, but for now, I'm going to save it in this file so we can take a look at what they look like. All right. This is going to take a few seconds to complete, but you'll notice that like most of the time it's taking here is on loop invariant inference. So it's looking at each of the like 5 signals that are written to in the loop body and sort of trying to build up this invariant piece by piece. So like assert that like one of these is equivalent and show that that's inductive, and then add the next one and add the next one and so on. And okay, so we're checking the 4th out of 5. Okay. This output, by the way, is because I passed the like debug flag. So if this wasn't here, it would just kind of sit silently for 30 seconds or whatever, and then print it out. Okay, there we go. Okay, so that took like 40 seconds. We built all of our loop invariants. We did all of the analysis, and then we printed out the verification conditions into this file. So let's take a look at what that looks like. Okay, so there's a bunch of stuff here. There's a bunch of like constant declarations and whatever, kind of boring, just to make the SMT solver happy. The actual VC is down here, starting with this assert. And so you can see that basically what it's doing is the invariance or the loop invariance has proven that the arrays are all equal or equivalent within the bounds of the loop. And so the remaining verification condition is basically saying that for all elements of the array not hit by the loop, prove them equal. And so, there we go. That's fine. So in this case, like you can see that you've got this like quantified for all, and then the actual implication that you want to prove has in the antecedent this like trivially false thing because there's nothing left to show, right? And so our SMT solver should like very easily be able to look at this and say unsat. And in fact, if I do Z3, if I pass this to Z3, Z3 immediately returns unsat. And so if you remember, unsat means that there's no counterexamples, and so we've like correctly verified this. On the other hand, if I change the bounds of the loop to not hit the entire array, so I have a decomposed product unsound dot LLZK. I have to, I guess, show you what it looks like. So the only difference between the unsound version and the sound version is now my loop, instead of going from 0 to 8, is going from 0 to 5. But the arrays are still of length 8. And so the loop is kind of building up the correct thing for the first 5 elements, but then not doing anything for the last 3 elements. Okay, so I'm going to run the verifier on this again. Gotta paste this in. Okay, so you can see here I'm running this on unsound, which has like the different loop bounds, and I'm passing, or I'm saving this in a different SMT file. So again, it's going to try building up the invariant piece by piece, and in fact, like every piece is still going to be inductive because like the loop is still like you're still sort of building up array equivalence across the loop. It's just that the final invariance that you get at the end isn't going to be strong enough to prove the post condition that the arrays are equal everywhere, because the final invariant is going to say that they're equal from 0 to 5. And so the verification condition is going to end up just asserting the rest of it, basically. In particular, what's going to happen is like we build this invariant, and then we're going to see that it fails to prove the thing. So we're going to strengthen it to also talk about the last 3 elements, but we're not going to be able to say anything about the last 3 elements. So that's what's going to be left over for the VC. Okay, so that took 46 seconds. Let me print these out. So again, you've got all of the like boring stuff, all of the constants or whatever, and then the actual VC is this assertion. But now you can see that the thing it's asserting is for all x that are for all x where x is not less than 5, but x is less than 8, right? So in particular, this quantifier is going to sort of visit values of x like 5, 6, and 7, right? And then like 5, 6, and 7 are exactly the things that are required to be equivalent in the arrays, but not visited by the loop. And so our SMT solver should be able to find a counterexample here. And so you can see if I pass this off to Z3, I get a result of SAT. And in fact, if you look at what the counterexample looks like, we can see that it's inequivalent because like you've got this definition for low 0, which at index 5 is 0, and you've got low C, which at index 5 is 1. So this kind of makes sense. Like the easiest way for these arrays to be unequal is for something to be unequal at index 5 because index 5 isn't being constrained by the loop. All right. So that's the weakest precondition. Let's take a look at the flattening pathway as well. So I have this cumulative sum example that I wrote. This is not doing anything terribly interesting. It's just you have an input array of 8 elements, and then you kind of build up this output of like sort of like prefix sums or whatever. And of course, you know, this is easy enough that like weakest precondition will just do the right thing, right? Generate the right things, pass it off to Z3, and it's fine. But just for fun, let's try this flattened. So again, I'm doing LLEQ verify, passing all this stuff in, and then I'm adding the flatten flag so that it can unroll that loop. Okay, and so here you can see that because it's been flattened, we no longer have like one array, we have 8 separate values, like 8 separate scalar values, but we've kind of proved each of them equivalent one at a time. I also have a version of this that is unsound. So you can see here, like the witness generator is still doing the right thing, but in the constraints, I forgot to add the input. So the constraints are just constraining the entire output array to be a constant. Okay, so if I run this through the verifier, you can see that it still shows out of 0 is equivalent because like that part was actually done correctly. Like the witness and the constraints are doing the same thing. But for everything else, it has a counterexample, and so it gives me a model here. Cool. Yeah. Okay. That's what I got for the demo. So I will, I guess, swap back over to my slides and finish this up. All right, and then all right. Can people see my slides?
Yep.
Sweet. All right. So yeah, so that's the demo. As I mentioned, LLEQ is open source. It is under active development. So here's maybe a few things that you can look forward to seeing coming down the pipeline at some point. First of all, we're hoping to get some better support for subcomponents. So right now, we do everything like modularly, one struct at a time. If the struct that you're verifying calls on some other struct as a subcomponent, there's sometimes like some issues with like aligning the subcomponent calls or whatever that can require a little bit of manual intervention. So we're hoping to get that stuff ironed out. More generally, we're working on some smarter heuristics for product program alignment. So as I mentioned before, like anytime you have loops, basically the only way that you can come up with a good enough invariant is if you've like figured out how to fuse like matching pairs of compute and constraint loops together. And so this is pretty important to being able to verify more complicated structs where the alignment might not be as obvious. And then finally, I think the interesting thing here is we're working on being able to express more complicated pre and post conditions on your structs. This is kind of related to the like verif stuff from last week. But for example, you might want to express like a precondition saying that your inputs aren't 0 or whatever, right? Because there's like a bunch of cases where the struct that you have might technically not be equivalent, but the only counterexamples come from something like a division by 0, which you don't expect to happen in practice. And so like this would allow you to express that to the verifier and then like avoid seeing these like sort of spurious like bug reports or whatever. Maybe more interestingly, you want to be able to express post conditions on a struct so that when you use that as a subcomponent somewhere else, you can use that post condition as like an extra fact to help you prove the parent struct correct. So this is specifically something that shows up a bunch with like num to bits or something like that, where knowing that num to bits is enforcing like a range constraint on its input can be useful in proving the equivalence of like some other component that uses num to bits. So yeah, like adding support or like adding integration with that. And then, yeah, as I mentioned before, LLEQ is open source. It's part of Project LLZK. I've got a link to the repository here. Again, I kind of mentioned this during the demo, but like all the stuff that I've talked about in the talk and everything that I've demoed is currently in this like public release branch. We are working on getting that merged to main, just pending some like code review. So hopefully that should be merged soon. All right, with that, I would like to thank the Ethereum Foundation for funding all of this work. And I think maybe I have time to take some questions.
Yeah, thank you. So I have one quick question. I see anyone else can feel free to unmute. Is I guess what the demo is pretty clear in terms of how it works, but I'm curious, what's the maybe biggest example that you've tried to run this on? You know, at which points does performance or like memory for the SMT solver start being an issue? What are kind of bottlenecks that you're seeing?
Yeah, so I think the biggest thing that like, or I guess I should maybe start by saying that in the repository we have a bunch of examples and like a script that kind of like runs all of these. So that'll probably have a more like detailed like concrete answer that you can look at or whatever. The biggest thing that probably like fully finishes verifying here is that like decomposed product template that I showed. A lot of the issues come from probably not so much the like size of the query necessarily, but the fact that the structs or the fact that the computations are doing like weird computations that are equivalent because of some like finite field properties that the solver has to spend a bunch of time trying to like rediscover. And so it just like proving that something is inductive or like proving equivalence along one particular thing might time out just because it's doing a lot of like complicated finite field arithmetic. And so we've sort of been working on some ways to like optimize the encoding for that. So like you don't always have to reduce mod p if you know something about the like interval that the inputs fall in or whatever. And like trying to build things up there. But yeah, I think right now the biggest bottleneck is trying to get an integer solver to discover interesting facts about like finite field arithmetic.
Also, there's like some large circuits that will verify really quickly once we have the subcomponent stuff done, like Poseidon or something, because our symbolic store should just be able to prove equivalence pretty straightforwardly. So you don't even have to discharge anything to an SMT solver. So it's a little bit like complicated whether the size doesn't necessarily correlate with sort of the complexity.
Yeah.
Any other questions? Yeah, go ahead, Albert.
Thank you. First of all, thank you for the talk. So I was curious about your first example in the demo, because I think it was the baby ad, no? Am I wrong? So
yeah.
What exactly you prove there? The equivalence between the constraint system and the witness computation, and for instance, the code in the Circum library. Is this what you prove?
Yeah. Although I guess it's worth noting that like because of kind of what I mentioned about the rediscovering things about finite field arithmetic being complicated. The solver here kind of times out trying to say anything about X out and Y out. But in particular, like it proves equivalence of all of those like intermediate things.
But well, I'm quite surprised because it relies on some properties of the elliptic curves that I really don't see how you can discover these using SMT solvers. So it's because you infer new properties or you put preconditions. What's the point here?
Yeah. So no. So that's a good point, right? So if you, I guess maybe maybe I could have chosen like better glyphs here or whatever. But the verifier proves the equivalence of those intermediate like beta, gamma, tau, and delta or whatever, and like those are in fact equivalent. The actual points like x out and y out are not provably equivalent based on the information that you have here, and so it fails to do anything. Like it fails to also find a counterexample.
Okay, so you in this case you cannot find because I mean it's very difficult, very hard to prove that there are no other deltas and tau. So I guess that this part is not covered. Okay, then fine.
Like that relies on
It was my failure, so I understood this wrong. So okay, good, thank you.
All right. Do we have any other final questions? Otherwise, we can end it a few minutes to spare. And then I'm kind of curious as well, how well is this playing with the LLZK spec language?
So that is the goal is to have these play really nicely. That is something that we are kind of starting to work on now. So that's kind of what I mentioned about like using the spec language to describe like pre and post conditions on the struct that you can then like use elsewhere when you're verifying things or whatever.
Yeah, that's what I was wondering. Because also when you're deriving invariants and things like this, it would be nice to be able to spit them out in the spec language so that I guess the human can look at it.
Yeah, absolutely.
Some of these you can also infer like through our range analysis, like the num to bits one. In a lot of cases, you can infer that that when just from a simple range analysis that your input is constrained to be within some range. So you don't necessarily need the spec language if your preconditions are typically ranges. But obviously like for more complicated, like let's say relational constraints, then you should use the spec language, and we'll integrate that soon.
Yeah, that makes sense. That sounds good.
Just a small curiosity. So I've seen some examples in which you use the num to bits circuit, and from our experience, solvers like Z3 or CBC5 struggle when you use a big number of bits. Is this the same in your experience or not? Or
that is the same in our experience, though.
Okay.
I think you can kind of get around it for the most part, because like num to bits is kind of proving basically that there's like so it depends. Like I think the trickiest case is obviously when the number of bits is equal to the bit width of your prime. But you can also like get around that case by noticing that it's kind of like lifting up to the integers. So you can consider the bit decomposition itself as representing some other integer that's being reduced mod p. And then that can, so we haven't done like this kind of lifting and lowering stuff in LZK or in the verifier. But if you can kind of like lift up some of these representations up to kind of like whatever higher domain, like the integers or whatever, then it makes the reasoning easier, because you can, in a lot of times, throw away the bits, right? Yeah.
So another option, that is maybe we talk and maybe because with our solver we can go up to 254. So maybe
that's a good
chance
option
for you to try to put it in your list of solvers, because I guess that you don't care. So after all, you only need an ansat or a sat. So I think that would be good maybe.
I think we will want to add that to our ensemble, but we just have to like kind of add the encoding.
Great.
Yeah.
Okay, let's keep talking.
By the way, how long does your solve? I started playing with it, but how long does it take to like, let's say, check like the determinism of num to bit strict? Like roughly.
It should be quick, super quick. If not, there is something wrong in the installation. I mean, for us in my laptop, it depends. When you reach
Let's say 254.
hundreds, when you get 100, you are in hundreds, then maybe you need 20 seconds.
But what if it's like, let's say 254 bits or something?
254, I mean, this one is the opposite because this is for proving SAT and this is hotter. And up to
No, I meant for the
253.
strict one. For the strict one,
The
it's
strict
like
one. But
Yeah.
the strict one is also tricky. We have to talk about that because the strict one,
Yeah.
you need the alias check, and then both things together. Okay.
Yeah, for the num to
maybe
bits for the non 254, it's pretty easy. But like for the 254, I guess I think, yeah. Anyways, yeah, but let's talk more because I think that could be
Yes.
interesting.
I think we
Okay.
are facing similar problems, and I think we can help each other.
Yeah, sounds good.
Great.
Right, then I think we'll write it down so we can pause it here. Recording will be on YouTube as usual. And yeah, thanks for the great talk. It's nice to see more and more progress happening on all these equivalence checking.
Thanks. And also we
Thank
welcome
you.
any PRs or any kind of like, yeah, feedback or whatever. Like, yeah, it's a definitely active development and it will be open. It's not like a proprietary Veritize tool. So, and it's also just, it's kind of like, we just sort of finished the development. So you should expect to see a little bit of like hiccups when you use it. So, but yeah, we'd welcome contributions and feedback. So thank you so much.
Thanks. Yeah, that'll be part of recording.